And let's get on with the presentation. First of all, let me introduce Dr. Ziqiu Xue. And Ziqiu is the chief researcher at the CO2 Storage Group at Japan's Research Institute of Innovative Technology of the Earth. So I've just got my screen now where you can submit the questions, and this is the go-to panel. And here's Ziqiu. So Ziqiu is very much a specialist. He's been working more than 20 years in CO2 storage aspects, particularly around geomechanics and geophysics, which makes him one of the most experienced researchers in this area in the world. And Ziqiu is, of course, very well known. Prior to taking up his role with RITE, he's had various other positions with Faculty of Engineering at Kyoto and also with Kiso Jiban Consultants Company. So Ziqiu has a Bachelor of Science and a doctorate in engineering from Hokkaido University. And with that, I would like to pass on the presentation to Ziqiu. So Ziqiu, the floor is yours.
Thank you very much, Steve. Hello, everyone. It's my pleasure to give a presentation on this talk, Microseismic Monitoring, the CCS field. I'm Ziqiu Xue, working with the CCS Institute of Innovative Technology for the Earth, we call RITE here. Today's talk consists of 3 parts. The first one is I would like to give a simple review on previous studies of fluid injection, because I think CCS had many similar issues as the geothermal oil fields. The second part is seismicity observations at the CO2 injection field, like Weyburn or Lacq in France. So at the last part, I will give a talk about the field surveys results at the Nagaoka after the 2 earthquakes hit the area in 2004 and 2007. We talk about the CO2 retention from the well logging and the close-wall seismic tomography. Also, we give some information about the cap rock and wearable integrators. So firstly, I will show the fluid injection previous studies results. This slide summarizes some previous study results, like stimulation, the production to the geothermal oil field. What I want to say is we exactly showed many common issues with geothermal or oil and gas field. But I want to point out is we should look at the rock. Look what kind of type of the rock or the reservoir. As marked in circles, I indicated 3 sites. The first one is a low frio, where the rock is classic sediment. And the second one is a clean county, which is rock type is a massive limestone. The last one is geothermal field, so the rock is crystal. So I like to mention is when we talk about the CCS, we need to keep in mind is the rock type in CCS is mainly the classic sediment, so it's not directly can apply the other results from the crystal rocks like the geothermal fields. So let's move to the summaries of the talk of the previous studies. What we learned from the previous study, like the field fluid injection. The first one is microseismic monitoring must be performed by downhole instruments due to the small size, because the magnitude of the microseismic is very small. The second one is most events fall in the magnitude -4 to -2 range from the surrounding the injection point. That means the cannot be propagated to the so far from the injection well. And also microseismic techniques equally useful if the sufficient events are observed in sediment reservoir. That means the microseismic information could be useful when we talk about the integrate of the cap rock systems. So from the lower frio, 2,900 events recorded, but they only succeeded to locate the locations, just 54. That means much of the events are too small for location. So this is very different with other two case studies, because other case studies they may record good signals from the massive rocks. And okay, let's move to the second part, the seismic state. It is a CO2 injection field. We show the two examples from Weyburn and Lacq. From the Weyburn CO2 EOR field, there are very good examples of the data sets observed during the CO2 injection. Here, this figure indicates that this square indicates the injection well, and this triangle indicates the observation well. So they have 8-level, 3-component geophone systems installed in observation well. And the distance between two wells, such as 50 meters away, CO2 injection rate with 100 to 50 ton per day from 2003 August to 2004 11. So let's look at the result recorded by the geophone system. So this figure shows the map and the east-west cross-section, the right side, views of the phase 1B event plotted by Dr. Verdon. Let's look at the first map. At the left side, we found the events here are colored with yellow, magenta, and the red. So the different colors indicate the different period. And if we look at the right hand, we find the reservoir is indicated by two dashed lines, with a very thin line, and the geophone system is over the reservoir, of course located in the installed in the caprock systems. We found even the red color circles are located around the reservoir, not inside, not always inside the reservoir. That means we still have problems, or they have to make progress how to locate the event. If the event, the signal of the event is very weak at the CCS field, to make more precise location procedures. And the next one is how far we can install the systems, because of the very small magnitude of the microseismic. So this figure plotted the event magnitude against the distance from the array. So usually at the CCS field, where we record the microseismic events, the magnitude is minus 2, the maximum is -2. So -2, that means we needed to put the system, the recording system, very close to the injection point. Like this figure indicates, if the magnitude is -2, this line, the straight line indicates the limit of detectability. We need to always locate or install the system very close to the injection point in the reservoir. So here is just a very simple summary about the microseismic monitoring at Weyburn CO2 EOR field. They recorded the event magnitude always ranged between the -3 to -1, even magnitude of -2 are still detectable, but over 400 meters away. And the comparison with the production date, the timing of events located in or just above the reservoir correct with the period temporary stopped injection. That means when we start injection or stop CO2 injection, the pressure changes, maybe the maximum pace in the injection field. And the third one is microseismicity occurs at the on-site of CO2 injection, and also appeared to correlate with period of increased injection. That means when you increase the CO2 injection rate, that may cause the drastic power pressure buildup in the reservoir. And the last one is events are characterized by a low dominant frequency, 15 to 8 Hertz. And the most important one is we have to challenge to locate this, the event with poor signal to noise ratio. Okay, let's move to the next one is CCS pilot site at Lacq in France. This is a case study to inject CO2 into depleted reservoir. They're quite deep. The depth is 4.5 kilometers. And at this site, the interesting one is they have a different system, not only the downhole system. So at the lower part indicated by the circle, by this square, network system composed of one deep array in injection well, and also 7 subsurface arrays in shallow wells, because we also need to the other like natural earthquakes or natural seismicities around the well, around the injection site. Also one surface seismometer in this field. So look at the result, the main result from the Lacq pilot site. They also recorded the microseismic events. The number is 6, and the magnitude is very small, minus 1.1 to minus 0.2. And we have to learn from this side is what we want to use this microseismic observation result. The interesting one is they showed a very important issue is the offshore alarm thresholds, because we like to use this microseismic result to set up the alarm system. So at Lacq, according to the magnitude and the number of events, the alarm procedures is activated. For the seismic events with magnitude above 2 in the circle given by the subsurface network, they have to give alarm. And for the magnitude above -1, if there is evidence of propagation in space and in time of seismic events external to the reservoirs, they also need to give the offshore alarms. So this is very important for us to when we want to use the microseismic monitoring system in the field. So in Japan, we are planning to start CO2 injection at the next large-scale demonstration site offshore. So the monitoring system will be a little different with the onshore systems. So this figure just to show you the conceptual diagram of the microseismic monitoring systems as the offshore we call potential storage site in Japan. So usually we put the observation, the downhole array system in observation wells. We also have the subsurface monitoring system like Lacq. And in Japan, we use the ocean bottom cable systems we call OBC. Use this system to record the events, including the natural seismicity and events or may caused by CO2 injection. Just one example, using the OBC system, we recorded a very small event offshore. The magnitude is 0.6, and the depth of the source is 100 kilometers, which is very deep. Actually, we usually inject CO2 into the just around 1 kilometer. So we are working with our observation, use a data set to record or to clarify if we can use this system to locate or to observe the events with very small magnitude. Also, this event will be located or occur in the very shallow depths, like 1 kilometers. So that permanent OBC system, ocean bottom cable system, enables us to carry out the 4D seismic survey. And also, we can use this system to start our microseismic monitoring. So there are already some examples using this OBC system to record the microseismic events in hydrofracturing. They record the magnitude is minus 3.0. So we believe this unique system may be interesting when we consider the microseismic systems at the offshore CO2 injection site. Okay, let's move to the last one. Last one is the field survey result at Nagaoka after the 2 earthquakes in 2004 and 2007. At Nagaoka, we installed just one geophone system at the surface of the CO2 injection site. The distance between the seismometer and the CO2 injection was just 100 meters away. So we inject CO2 into the reservoir at the depth of 1.1 kilometers. I think most of you may have some information, already have some information about the CO2 injection results at Nagaoka. So next figure indicates the geophysical monitoring system, including earthquake safety surveys. At Nagaoka, we started CO2 injection in 2003 July, and ended CO2 injection in 2005 January. So this figure indicates the CO2 monitoring issues. We use close-to seismic tomography, also perform the geophysical well logging very frequently to observe CO2 breakthrough at the observation wells. In 2004, October 23, during the CO2 injection, we had an unexpected event. It's because of this earthquake hit this area during the CO2 injection. So after this earthquake, we stopped CO2 injection for a couple of months to perform carefully the field survey, try to learn more or learn something about what happened to the CO2, the CO2 which we inject into reservoir. And when we stopped CO2 injection, we already have another event. It's in 2007, July 16, which is the second earthquake also hit the similar area. So this figure shows the pressure change, because pressure change is very sensitive. If some new fractures formed in the reservoir, the pressure decay curve may be quite different in the subsurface. So we compared the two decay curves. This one indicates the decay curve just after the earthquake, because the earthquake hit the area and the power automatically shut down. So this is a good example to compare with the left one. Is we stopped this CO2 injection in this case. Look at the two decay curves. We find there's no clear difference between the two curves. That means even as we hit the area, we couldn't find any difference in pressure changes. The pressure change is recorded in both ways. One is CO2 injection well, the red one, and the second one is the blue curve observed at the observation with number 4. Because we have system record the pressure change during the CO2 injection at the formation layer. So just want to show some results detail about the first earthquake in 2004. The main shock is 2004 October 23. The magnitude 6.8. The depth of the epicenter is 10 kilometers deep. The seismicity intensity is 7. The CO2 injection was automatically stopped at the main shock. So we have we have two pictures. The first one is shows some damages we found at the access load to the injection site. We also installed a CO2 detector to detect the CO2 leakage at the surface, the ground surface. Of course, there's no any CO2 leakage detected by this system. And at the right part, we show the CO2 injection site here, and the earthquake in 2004 is hypothetical is here, just 20 kilometers away. This way is onshore. CO2 injection restart when we've completed the surveys after the earthquake in 2004. So some results here indicate the what we observed at the Nagaoka with our geophone system. The left one indicates the main shock recorded by our system, EW, NS, EW, and up down. So the earthquake forms is very clear recorded. We also found the maximum acceleration recorded in EW direction is 705 G, which is quite high. That means the ground motion is quite high. At the right hand, we also plot numbers of events from 2003 March to 2006 March, which is just 3 years. This bar indicated the earthquake in 2004. We found this system recorded many events after the earthquake. So this histogram of microseismic events recorded at this injection site is from 2003 and also the 2005. Of course, the earthquake, the events in this diagram also include some events, not the always the natural earthquake, also include some surface noise. So it will be important topic is how to remove the noise or the natural earthquakes when we talk about CO2 injection may cause some microseismic events. So this figure indicates we already removed other events like the natural earthquake or noise. So what we plot here is just restart CO2 injection after the earthquake. And also here is we end the CO2 injection. And even when we end the CO2 injection, we also recorded the events at the site for about 1 year. We found mostly the events recorded just after the CO2, after the earthquake, and when we plotted the total events, we found some of the events we call likely events. Likely events means it's difficult to say this event is earthquake, natural earthquake, or microseismic event caused by CO2 injection. So we call likely events. Likely events appeared just after the earthquake. So we like to know what is the reason we recorded the likely events at this CO2 injection site. So we plotted the likely event from the starting CO2 injection to middle Niigata earthquake, which is in 2004. So we found there are 15 events here. So when we make it clear for investigation, we found this events there are noise, not the microseismic events. So we also found other 7 events here in different colors. We like to make sure what is the difference between these 7 events. So in Japan, we have very good system recording the natural earthquake. So we compiled our result with HINIT data. HINIT is good system in Japan. Recorded earthquake events here. We found if the event had a good match with the HINIT data, that means the event is earthquake, a natural earthquake, not the likely event, or the events caused by CO2 injection. So we indicated the circle here is matched event, and looked at the other 5 events were also compiled with hydrophone data, because we also installed 24-level hydrophone system in opposition wells. Of course, the hydrophone just recorded the events, couldn't provide the PS waveforms, also the S waveforms. We found the green circle. We find it matched with events matched with hydrophone record. Also, they have the phase lag in PS waves, possibly. So this event is these events are seismic events. The other 3 events, no recording hydrophone or no phase lag in PS waves, or they are noise. So even we have some possibly seismic event at Nagaoka, also the huge earthquake hit the area, we like to also know the CO2 maintenance in the subsurface. So we performed the seismic geophysical logging. So I just pick up one slide. Is here the sonic logging data. We plot the time-lapse change of the CO2 bedding zones here. The first 2004 is here. So we can compile the CO2 bedding zone. What happened to CO2 bedding zone before the earthquake, not after the earthquake. Or we also can repeat the similar survey to the earthquake in 2007. From this figure, we find there's no clear difference between the 2 data sets. So that means there's no any CO2 leakage or CO2 migrate from the reserves to other layers here. And another data is the crossword seismic tomography, because the logging data may provide you the vertical profile, but the crossword seismic tomography will provide you the date plotted in cross section, so we can make more detail about the Kepler integrators. We plotted this figure here. We can combine this figure with this figure, this tomogram between the 2 tomograms. If any CO2 leakage from the reservoir, this result may indicate some CO2 signs, the signs of CO2 leakage in Kepler. But from this figure, we couldn't detect find any difference between the 2 tomograms. We also looked at the integrate of the Weyburn. So we have many data sets about the because we have been aware for a long time about the cement evaluation, cement degradation. So USI ultrasonic image systems provide the cement evaluation, especially the casing to cement bond quality. So we brought 3 data here. The first one recorded 2001 USI, 2005 USI, and 2011 BHA TV. So this maps indicates the impedance of the recorded by the USI and the BHA systems. So usually the white colors or this contrast indicates the low impedance. That means low impedance sometimes means there's some microannuals in the cement, or the boundary between the casing and the cement, the casing cement. And we found that there's no clear difference between the 3 data sets where you recorded the Nagaoka. Even at the CO2 bearing zone, the cement is quite is also in good quality. Even the CO2 breakthrough observed these wears for 8 years. So we also confirmed the quality of the cement at this site. So a simple summary of the field surveys after the earthquake in Nagaoka. We like to say events with low signals after the earthquakes. Earthquakes indicate the safety, the safety of the CO2 storage at the Nagaoka site, and there's no signs of the CO2 leakage from the reservoir, and no damage in caprock and the wearable systems, evidenced by the formation measurement results, also the results of geophysical well logging and the close-to seismography, and from the ultrasonic image and borehole BHA TV surveys also indicated that there's no clear change in cement, even at the depths where the Class A cement has been exposed to the CO2 for about 8 years at the observation wells number OB2 and OB4. Thank you very much. That's all my talk.
Thank you very much, Ziqiu. That was great. I mean, you showed a couple of excellent examples from both natural occurrences of these massive earthquakes, magnitude 7, and its effect on a reservoir. It's a unique opportunity to see that. I don't know if it's a good opportunity or not, but it certainly was unique, and also the effects of our injection on seismic activity in the subsurface. So we've received a few questions along the way. I'd kind of like to maybe start out with things just off the top, though. Just to contrast an area like Weyburn, which is very tectonically quiescent, it's a mid-continent, versus Japan, which is obviously the other end of the spectrum. If you were to design a storage site, what kind of timeline would you look for collecting baseline data for microseismic? I think most of the examples we have, the microseismic, the geophones and so on, are installed not too much before injection or even after injection has started. But if you were to start it at a time when there was no injection or before injection, how much time do you think you'd need to get a good estimation of what background is?
Yes, we actually talked about this baseline surveys before the CO2 injection with Japanese experts in earthquake areas. They mentioned at least you need to have the baseline data set at least 3 years. But 3 years is not the exact one, because that's the period. How long certainly depends on the microseismic events, how active it is in the area. Because in Japan, we always have many natural seismicities here, so they recommend us at least you need to record the baseline events at least 2 or 3 years. Just a recommendation from the experts.
Yeah. Okay. Well, we have on that something you talked about. We have a question from Eros Artuso, and he's wondering if you can link the earthquakes to the microseismic events that you've recorded so far.
Yeah, and usually at the CO2 injection site, what we have to pay attention is just the pressure buildup due to the CO2 injection. And at the Nagaoka, we have 2 transducers. One is located in injection well, one is observation well. So we use this 2 data set to calculate this the pressure changes against the distance from the injection well. It's just one figure here. If we assume when we assume this is the maximum buildup due to the CO2 injection at Nagaoka is around 2.5, less than 3 megapascal, we find the pressure decay was it's exponentially decreased against the distance, because even the pressure buildup is up to 3 megapascal, but if you measure the pressure change just 1 kilometer away from the injection well, you will look at a very small one. That means the small pressure buildup recorded in the other areas. So we need to know the how the pressure impact of the pressure buildup surrounding the CO2 injection well.
Yeah, okay. Well, that also, I think, explains that. Cedric Francis has a question here about what do you think happens at the injector that causes the events? And it sounds like, to some degree, you've explained that, but maybe you could just follow up again and reiterate what happens at the injector that seems to cause the microseismic events.
Yeah, we need more data sets, because right now, I think there's no fully data set to make discussion about this issue, CO2 injection cause microseismics or not. Especially to the when we inject CO2 into the saline aquifer. So we are working with BEG, Texas. At the ground feeder, we placed a system to the subsurface to record the events during the CO2 EOR process, because if we want to make sure CO2 injection cause microseismics or not, we need to collect the data in very silent area. Silent area means is less natural earthquakes occurred that area. So we try to work with BEG about the CCS about the CO2 injection may cause microseismic or not.
Mm-hmm. Well, we have a question from John Bear, who wants to know what evidence is there that the Nagaoka earthquakes were either induced from CO2 injection or were they related to natural seismicity? So I'm assuming he means the large magnitude 7 earthquake, which was down about 10 kilometers depth. So maybe you could explain to him.
Yeah, yes. At Nagaoka, we have two earthquakes. First one in 2004, and the second one in 2007. People have concerns about the earthquake may caused by the CO2 injection. But remember, we inject CO2 just 1 kilometer depth in the subsurface. The earthquake, the location of the epicenter of the earthquake is 10 kilometers depth. So it's quite different layer, a different system. We don't believe, and nobody believes the pressure buildup, the impact of pressure buildup due to the CO2 injection may cause such large earthquake, magnitude up to 6.5 or 6.8. It's quite clear, I think.
Mm-hmm. A question from Mark Trupp about the 3-year baseline, the requirement for a 3-year baseline for natural seismicity. Do you think this would be less in a quieter region? I mean, is that 3 years in Japan, but in, say, Weyburn or some other area where there's nowhere near as seismically active, do you think 3 years is still an appropriate number?
No, I don't think so, because as I mentioned, we need to know the microseismic activities at the potential site, because how long we have to record the baseline data depends on the activities of the natural earthquake around the area, I think.
Yeah. Okay, a question from Jimena Schultz about the monitoring arrays themselves. For a commercial scale project which have very large CO2 footprints, how many wells do you think need to be used to monitor effectively, given that they seem to be the monitoring array needs to be fairly close to the source of the microseismicity?
And I think from Weyburn, we can find if the magnitude of the Earth, the microunit is very small, like -2 or -3. So usually or hopefully you need to install the geophone system very close to the injection well. But if the distance is too close, you may record much of noise. So you have to make the good estimation how far is good for you to install the geophone systems to this injection site. So I think you need to do some theoretical surveys with the geological model. If you assume some event is -4, and in this geological structure, if you put the system is 100 or 500 ways, how strong the signals you can record by your system. This is my recommendation.
Mm-hmm. Yeah, one of the things that Weyburn I noticed that they did find is that a lot of there's some microseismic activity associated with as much associated with production well as an injection well. So it's both the injection and kind of removal of fluids, which has some impact on some of this, obviously. And one of the questions we have here, again from Cedric, is can you think of a way to test if CO2 injection triggers microseismicity? I think some of the anecdotal data indicates that it does, but you see, is there a way to test that?
Yeah.
Okay. A question from Mark Truck. Have you seen any evidence of fault reactivation by monitoring near known faults?
Yes, at Nagaoka, during the geological survey, we are very careful to detect, for example, to try to avoid the fault systems around the area. I think the pressure change, the impact pressure change is just very limited in a very small area or narrow area. So when we are planning the CO2 injection volume, so how much CO2 we are going to inject at this site, we estimated the pressure build-up, and also from the geological survey, because this site has been explored by the oil company, INPEX. They have much data set about the geostructure, also the fault systems. At Nagaoka, we just inject 10 kiloton CO2. So as we estimate before the CO2 injection, the pressure build-up is very small areas. Couldn't give some any impacts to the fault system, which is quite far from the CO2 injection site.
Right. Well, I think we're getting close. Maybe one or two more questions is all we'll have time for. But one I'd like to know about is there's been a couple of studies recently that have used crystalline rocks as a proxy for the behavior of sedimentary rocks. And you talked a bit about that earlier on. But I guess I'd like to ask you just more clearly how appropriate is it to be using these crystalline rocks to model the behavior in a sedimentary system?
Yeah, I think the mechanism of the microseismic events in crystalline rocks and the sedimentary is a little different, because actually the magnitude of the microseismic event is strongly depending on the scale of the we call micro fracture. In the crystalline rock, usually we can record the high energy. We call people call acoustic event AE, and then that's it. The AE usually people can record by in this crystalline rock is the rock is very brittle, but if we look at the sedimentary rock, compared to the crystalline rock, the vertic fracture is not so strong, I think, compared to the crystal, like the granite rocks. So I mean, what I mean is the magnitude of the microfracture in between the two rock types is quite different. That's why we can just record the very low signal or poor signals in sedimentary rocks, and they couldn't also very difficult to locate the events in the sedimentary rock. But it's it's a granite, the crystal rocks, you have the good signals. It's easy to perform the location of the microseismic events. And that's the difference between the two rocks.
Okay. Well, I think we have a few more questions, but I think we're starting to run out of time, Ziqiu. We've got to give you a bit of a break. But we will certainly try to continue this conversation with Ziqiu and send out any responses that we need to. I just want to remind you that you can still submit questions also through the webinar inbox at webinar@globalccsinstitute.com, and that this webinar has been recorded and will be on the website in the next few days. So I guess as you're leaving also, we put together a quick 2-question survey, and we'd really appreciate it quite a bit if you just complete that for us to help us with this program. And I hope that you found this webinar useful, and we're open to any ideas for other webinars, of course. But I especially want to thank Ziqiu Xue, Dr. Xue, for presenting this and taking the time out of your schedule to answer questions and provide this really interesting and unique data set that was quite pertinent at the time. So thank you very much, Ziqiu, and thank everybody else for your attendance, and goodbye.
Thank you.